Let's look at how our model performs in learning the y equal to 1 by x plus epsilon function. With the training loss, we see that our model learns, but on the testing set, we see that the model does not perform that well. The errors are the highest between the values of 0 to 1. To look into the model, let's visualize the ReLUs. Visualizing the thresholds and the slopes of the ReLUs, we see that a lot of them are bunched up between 0 to 1, even though the errors were the highest here. So, to quantify this, let's plot the cumulative distribution of the thresholds. Here, the x-axis represents the threshold values, and the y-axis represents the proportion of thresholds below the corresponding value. We look at the red line, which is the final cumulative distribution of the thresholds. Specifically looking between 0 to 1, we see that around 80% of the thresholds are being dedicated for the values between 0 to 1. Now, this is because the slope of the function 1 by x plus epsilon changes infinitely many times here. And since ReLUs are linear and provide a single slope, we would ideally need infinitely many of the ReLUs to fit the 1 by x function. What would happen if we take other activations which were more nonlinear? We see that even other activation functions learn, but they do not perform that well on the testing set. Let's summarize our findings. So, we know that it is possible to fit a 1 by x type of function with neural networks because they are universal function approximators. We'll do a deep dive into universal function approximators in the upcoming day. But practically, these networks would need infinitely many resources to efficiently fit the 1 by x function. So, if it helps, it's best to have a dedicated microcircuit towards normalization. In the next section, let's look at an example of normalization.